We've contrasted volume integrals in cylindrical, spherical, and rectangular coordinates. Volume integral for a sphere of radius r. We've looked at mass integrals in terms of a density function 12 minus 9 rho over r, which we could express in cylindrical or rectangular coordinates. We obtained these integrals, each with its advantages and disadvantages, and we posed a question: what do we do for moment of inertia? Now, we've previously found the moment of inertia about the z-axis in spherical coordinates. So moment of inertia about the z-axis, and we'll call that, well, we'll just call that I for the moment. Okay, we've found that in spherical coordinates, mass times, I'm going to call it RAD, radius squared, to a volume increment. The distance from the z-axis to the point rho theta phi is rho sine phi, so that our integral of delta dv times this radius squared becomes our integral of delta times quantity rho sine phi squared with respect to v, and then we expand this out into triple integral and write out our volume increment, giving us integral from 0 to r, and we want to do that integral first, and then from 0 to 2 pi, and finally from 0 to pi, not r. Our delta function is going to be 12 minus 9 rho over r multiplied by rho squared sine squared phi multiplied by rho squared sine phi d rho d theta d phi. Okay, we've seen and performed this integral. If we want to do this in cylindrical coordinates, then our distance from the z-axis is just the r coordinate. Okay, so any r theta phi, r theta z is at distance r from the z-axis. And it follows then that our integral of mass times distance from the axis squared is going to become the integral of delta times r times dv, and that's going to end up being a triple integral over the familiar limits of 12 minus 9 square root of r squared minus big R squared minus little r squared over r of r times r, now integral with b with respect to z, dr d theta And unfortunately I'm having to compress that quite a bit, but I'm going to rewrite all this on a different sheet. So that the essential thing we need to see here, we'll worry about the order of integration and the limits on the integral, is simply that we're integrating our density function multiplied by, and it's not r, it's times r squared. So it's times r squared, then times our volume increment r dr d theta. So that this is like the density, volume, and the distance from the z-axis squared. In rectangular coordinates, our distance from the z-axis is simply the square root of x squared plus y squared, so that our integral of density dv times that distance squared becomes what? Well, it's going to be the integral of quantity 12 minus 9 square root of x squared plus y squared plus z squared over r times r dv times r radius squared. Our distance from the axis squared is going to be x squared plus y squared, and our volume increment is going to be right now I'll just write it as dx, dy, dz. This will be a triple integral and that's getting to look pretty bad, but we get the idea. So that our three possible integrals for the moment of inertia, the moment in spherical coordinates, integral from 0 to pi, 0 to 2 pi, 0 to r of our density function, multiplied by the square of our distance from the z-axis, multiplied by our volume increment, rho. This integral is with respect to rho, with respect to theta, with respect to phi. So it's rho squared sine phi with respect to rho, with respect to theta, with respect to phi. And that's our moment of inertia. Similarly, we could write the integral in cylindrical coordinates. Our density function is going to be 12 minus 9 times the square root of r squared plus z squared over big R. Our distance from the z-axis is just going to be r squared, and our volume increment is going to be what? R dr d theta dz. And let's be careful about the order in which we integrate. Remember that our description of the region has z running from two limits that depend on r. So we're going to integrate with respect to z first. This r is part of our volume increment. Our z goes from negative square root of big R squared minus little r squared to the square root of big R squared minus little r squared. And then we'll integrate with respect to r and with respect to theta, so that we have our entire volume increment here, just as we do up here. We have our distance from the axis squared, and we have our density function.